So we know what is eBGP now and what is IBGP. In the lab, we saw the peering between routers which are in two different autonomous systems is eBGP. It need not to be only pairing with two autonomous systems. It can be with many autonomous systems. See, if you take this picture here, we have here one eBGP, another eBGP. I may have another one also. Many. That is called multi-homing, right? More than two routers forming neighbor is multi-homing. So eBGP is well explained. I was telling you that eBGP need to be directly connected by default. Whereas for IBGP to form neighbor between this router and this router, there's no need for BGP to run here. We saw that in the class. All that they need is they need reachability. For that we use some IGP protocols that will be used to reach. We have to use IGP protocols for internal networks reachability. So we make use of the same reachability to form peering. We saw these things in the previous class. Same thing we are going to repeat here theoretically. What is BGP peers or what is BGP neighbors? They are nothing but routers that can establish three-way handshake. This is what I'm planning to show you using Wireshark. That's why we are going to go back to the same lab, yesterday's lab. If two routers can negotiate successfully and complete the three-way handshake, they can now continue negotiating using BGP and form adjacency, neighbor. Any two routers that have formed TCP connection to exchange BGP routing informations are called as BGP peers or BGP neighbors. Very important is they need to have reachability so that TCP connection can be established. When we say TCP connection, it means three-way handshake. Say an X router or eBGP here. C is in 65500, X is in 65100. So there are two different autonomous systems. The neighborship is called as eBGP. Similarly, D and Y are eBGP neighbors. Now, if you see, eBGP neighbors by default need to be directly connected. This is what I was talking earlier. The real meaning of this, you will know later only in another one day class. Now you may think, I know what is directly connected. See, this wire is connected directly. And I need to give this IP address. Let's say this IP address is 1.1.1.1. This IP address is 1.1.1.2. Fine, I'll go to X and say 1.1.1.1 is neighbor. I'll go to C and say 1.1.1.2 is neighbor. And you know that this is what directly connected. I do agree, yes, that is what it actually says. But there is also more in-depth meaning to understand, which is not necessary to understand now in this level of BGP study, there's much more to learn. Then we will see the other meaning, other in-depth meaning of the same word, directly connected. It's coming later. I'll remind you when we go there. So, BGP neighbors by default need to be directly connected. There's nothing but EBGPs are nothing but the BGP running between neighbors that belong to different autonomous system. So EBGP stands for External Border Gateway Protocol. Next is the Internal Border Gateway Protocol. Internal Border Gateway Protocol. IBGP. Internal. The main difference is, see the last point there. IBGP peers do not have to be directly connected. These are BGP running routers within an autonomous system. Within an autonomous system. All right. This and next 2 pages are going to teach us very important fundamental of BGP. This and next 2. This 3 pages are same topic. 3 pages that we are going to see deals with same issue. Not just 1 or 2 points you are going to learn from these 3 pages, at least 4 points. We'll be learning about BGP. Fine, what is here? See the same topology you'll see in the next page as well as this page. So I'll be jumping between these 3 pages to present it well. Let's say A has got a network. And F wants to send a packet to network, which is there in A. Yeah, so A has got a network connected, let's say, on F00. Someone here called Abraham. Now, someone from here wants to ping Abraham. The someone is 2 autonomous systems away. Not just 2 routers away, it's 2 autonomous systems away. Now first thing is we need a protocol to bring routes from one autonomous system to another autonomous system. That's why we use BGP. No other protocols do this. We use BGP, we trust BGP to do this because BGP is more secured, with a lot of attributes. No other protocol has got those things, so we don't like to use other protocols. We use BGP. So via BGP, this network 10 should be advertised. Router A advertises to B. And a few minutes before we learned that, in the previous chapter, in the previous class lab, we learned that B can form IBGP neighbor directly with E without having BGP on every hop. If you notice here, D and C don't have any border gateway protocol. No border gateway protocol is running here. B can ping E because there is OSPF providing the reachability, using which IBGP is already established. So when A router advertises about Abraham's network 10.0.0.0, B delivered it to E and E delivered it to F. Now F in its routing table knows route to reach 10 network. It will send it to E router. So F has got the route in the routing table using which the packet now can be forwarded. But when the packet goes from here to E, E will forward it to C because it needs to go to B. Can E jump directly to B? No, there is no physical connection. There is no physical connection between B and E. No physical connection. There is a direct IBGP peering, but that peering is via these two paths. So if packet arrives to E, you have to forward it to either D or C in order to reach B. Suppose it goes to C, what C is going to do is it's going to check the routing table. Check the routing table for 10 network. Will there be route for 10 network? No, because we did not learn other autonomous system networks on D and C. We don't run BGP, so D and C never learned. DNCs have never learned those external routes, those other autonomous system networks. DNC have never learned a 10 network. So what will happen is packet gets dropped. This is what we call it as black hole in networking. Why it is called as black hole in networking? Here it is very small topology. You say packet got dropped in C or D. But in a large network, you will not be able to identify where it disappeared. When it is dark, deep pit, can someone say where the coin is located? Deep in a well, dark well, not possible. If there's a big well and a coin got lost and it is too dark, it's not easy to locate because it is dark inside. Likewise, packet is coming from E to B via D or C, but D and C don't know, so they drop it, they discard it, they cannot forward it. Now, what do you understand from this? We need to know a solution. There are various solutions to this problem. We understand one thing, that C and D don't have roots, so they dropped it. We somehow need to bring route here. And you may suggest to run BGP like this, so that all the routers will learn 10 network. Because there is no BGP here, and here you don't have the network. So now you started thinking that I should have BGP in order the ping to happen. You're right. That is one solution. Now you are getting a reason why I should run BGP here and here, so that the BGP updates will also come and update the routing table here. As it is updating in E, it will also update in, it will also get updated in C and D. That's the idea. Yeah, that's the idea. So you're thinking that the packet got discarded because they don't have root, because they don't have BGP, they don't have root. So we need to run BGP on every router. That's what you are thinking in your mind. That is one solution. I'm not denying that. But there is a better solution, which is not solution with BGP. We have a solution with GRE or MPLS or VXLAN EVPN. Some tunneling techniques can be, some tunneling technique like GRE will help. So now you no need to have BGP here. No need to have BGP here. Tunnel will take care of this. If E wants to send it to B, using tunnel it will go boom like this. Even though tunnels are using C and D, doesn't matter for us because it is tunnel, it will go there. It won't check the routing table of C and D. It won't check the routing table of C and D to reach 10 network when you have tunnel. When you have tunnel, E will look for B and B will look for E. That is there via OSPF. There will be additional encapsulation. That is what tunnel is. Additional encapsulation. If you don't know much about tunnel, we'll talk later. Now, but this is not a BGP based solution, so we will not talk about this more. We'll talk later when we are in GRE class. These two routers, they successfully delivered the update, but still we are not able to ping because there is a drop in the middle. The middle routers don't know the root. And one of the solution is this. What is that? Redistribution. You can take BGP root and give it to OSPF. And from here, you can take OSPF and give it to BGP, and BGP will give here. This is one way, but very, 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 very bad way. Not recommended. Why not recommended? Why it is not recommended? See, we don't have BGP here, so we will not have routes from A network and F network. To learn them, we are copying that from BGP to OSPF, so that via OSPF it will go here. That's our idea. But it's not recommended. It will work. It will work. Not recommended. Why? Why it is not recommended? You see, we Enable BGP for a very important reason. What is that? One is security. BGP is more secure because it is TCP based. Secondly, it has got attributes, which is very important between the borders. But when you redistribute, what will happen? And again, when you redistribute from OSPF to BGP, what will happen to those attributes? All lost. Because OSPF cannot understand attributes. OSPF knows only one thing called metric, cost, based on bandwidth auto cost, or metric that you may manually configure as a cost. Other than this metric, OSPF don't know anything. So we lose our important message that sent along with BGP updates when we redistribute. Those attributes are very important. That's why we have BGP here. When you are going to drop all the attributes on B and E router, what is the use of we running BGP? You should have run a simple protocol. There's no need for BGP if you are going to redistribute like this. It will work. It is a networking solution, but not a recommended solution. Unfortunately, many are doing this as a solution. Many are having this as a solution. They want their network to ping, that's all. They don't think all these things. We need reachability, redistribute, boom. We got the routes, we are pinging, finish. And they don't understand that we have not used BGP effectively. So, redistribution is not a good idea. The best one is not in this chapter. We already discussed that we need to put a tunnel. Put a tunnel between B and E, which is also widely seen in big ISPs. We use MPBGP, IPv4, VPN tunnels. We call it as MPLS Layer 3 VPN. That's a very good idea, which we see in most of the places. Big ISPs, small ISPs, they all do that. But some poor people, they don't realize that they are doing a mistake. They simply redistribute. Not good. Now we are going to understand the same scenario with a different perspective in the next page. See, so far we have seen redistribution as one solution, not recommended. Tunnel as one solution, not in the scope of this class. Now, in the scope of today's class, this is what we have. What is that? Run BGP on every router. But when you run, how you should run? You see, in all these 4 routers, we have BGP OSPF, BGP OSPF, BGP OSPF, BGP OSPF. Even here, if you see, in all these 4 routers, BGP OSPF, BGP OSPF, BGP. What is the difference? The difference is, here we are running BGP on all 4 routers. Here, we are running BGP on all 4 router. The main difference is peering. Here we are peering with D and C, and D is pairing with E is pairing with C, but it is not pairing with E. There is no pairing. Why? Because we think that why we should pair with E now. When we are pairing with the C and C is pairing with E, we think why there is need for pairing from B to E. That's our thinking. So we did not form peering with E. BGP is running on all router, but peering is not done with all router. Peering is done only to those routers which are immediate adjacent, physically connected, physically available. We don't accept it as full mesh. Even though you are running BGP on all router, you don't accept it as full mesh. It is only partial mesh. Why it is partial mesh? Because all are not neighbor with everyone. If every single router form peering with all other router, then it is full mesh. You see, here there is no neighbor between D and C, B and E. Here you have neighbor with D and C, B and E, as well as B and D, D and E, B and C. Lot of peering you see. This is what we call full mesh, peering with everyone. So in B, how many IBGP neighbors will be there? In B, in full mesh, 3 IBGP neighbor. Likewise in D also, 3 IBGP neighbor. In C router also we will have 3 IBGP neighbor. In E also we will have 3 IBGP neighbor. Whereas here you have only 2 IBGP neighbor. 2. In B also you have only 2. Now, why should I form neighbor with everyone? Listen, I just got 4 routers. What if I have 100 routers? Then this router will have 99 neighbors. This router will have 99 neighbors. Whereas here, even if you have 100 routers, you will have only 2 neighbors, physically connected neighbors. Listen carefully. Here, if I need to form full mesh, I need to maintain 99 sessions on every router. 99 neighbor I need to send to keep alive. 99 neighbors I need to send update because TCP based. Think about the process utilization of maintaining and sending keep alive and updating the new packets with the attributes. Not easy. Full mesh configuration also not easy. 99 neighbors you need to configure. Whereas partial mesh is only 2 neighbors. But the problem is, only when you have full mesh, it will work. Sorry. Even though you got BGP on all this router, there is a problem. What is the problem? Let's say I got 10 network here, Abraham's network. It goes here. It will even come here. But this 10 network will never be given to this. Will not give. C will not give. Even though C and E are neighbor, even though these two guys are neighbors, even though D and E are neighbor, D will not give. Because that's the policy. You see here, by default, routes learned via IBGP or never propagated to other IBGP peer. Please try to understand this word. Route learned via IBGP. How the router learned about the network? It learned via IBGP. Who is that IBGP for D? B router. Same way C also learned from an IBGP. And what is this rule says? Route learned via IBGP are never propagated to another IBGP. It won't be given to another IBGP. If you have a EBGP, it will go. Route learned from an IBGP will go to EBGP, but it will not go to IBGP. So what is the solution? You make full mesh, meaning you ask B to deliver a copy directly to E. For that, what is needed? You need to form an IBGP with this guy, which is missing here. Only when you have IBGP peering directly with this guy, B will directly give to E. So in order to solve this problem, in order to solve this limitation, we need to have full mesh. Why do we have this limitation in first place? We'll talk about that later. But now my question is, did you understand this limitation? And did you understand why we need to have full mesh?
Yes, sir. Because as it says, by default, route learn from IGP does not propagate to another IBGP. So we need full mesh for the route to be propagated throughout.
Yeah, we need full mesh to propagate the route directly to all other routers, so that the middle routers need not to propagate. Even if they try to propagate, not going to be allowed. So all can talk to all other direct. Everyone, each one of the router, each router can directly go and give a copy of update to everyone. For this, we need to have full mesh. Now, what is the problem in this? Maintaining session is the problem. As I said, if you have 100 routers in this autonomous system, you need to talk to 99 neighbors. 99 neighbors you need to maintain, keep alive, send all the updates with attributes. Oh, that's going to be a scalability issue. Yes, it will impact the scalability because the router is too busy in taking care of the BGP updates and neighbors. So what is the best solution? That's what we discussed here. Put a pipe between B and E. Put a tunnel. It can be GRE tunnel. It can be MPLS layer 3 VPN tunnel or a VXLAN tunnel or any sort of tunnel that you want to do. You can use. No problem. Any tunnel is okay. MPLS layer 3 VPN is what you will see in ISPs. Now, we are coming back to this same limitation. Why is this limitation in first place? Why you have this rule? Because of this rule, only this big problem arises. What problem? This full mesh problem. Instead of forming just 2 neighbors, we are forming 99 neighbors when you have 100 router. This 99 router maintaining is because of this full mesh, because of this limitation. Why do we have this limitation in first place? What is this limitation called as? They simply say by default route learned via one IBGP. What is the name of this? This is what called as IBGP split horizon rule. This is not the split horizon that you have on the physical interface. This is not the split horizon that we learned in RIP protocol. This is not that IGP related. This is IBGP. This is what called as IBGP split horizon rule. IBGP split horizon rule says the route learned via IBGP are never propagated to other IBGP. For this reason, you need to have full mesh. Now, again, I'm coming back to the same question. Why, first of all, we have this IBGP split horizon rule? For that, I would like to draw a diagram and explain. Don't focus on that picture. Let's take this picture. Same 4 router I'm drawing. Same 4 router I've drawn. But I'm going to do a slight variation in the topology. What is that? Instead of connecting wires like this, let's say I got a switch. I'm connecting like this. Mostly we'll have like this in the environment. Mostly we'll have environment like this only, connecting through a switch. All the routers will be connected through switches. And you will have multiple VLANs. What if there is no VLANs? What if there is no VLANs between this 4 router? Now they are going to be in single broadcast domain. According to layer 2, they are going to be in single broadcast domain. Same VLAN. IP address may be here 10.12.0.0, 10.12.0.0, and then 10.13.0.0 sub interface, something like that. Okay, so this is how we do physically. In layer 3 there is no issue, but the problem is there is a layer 2 issue here. So how BGP solves the issue? See, what issue? Network is coming. Who are all neighbor here? BGP neighbors. According to what we saw, if it is not full mesh, these 2 guys are neighbor, and these 2 guys are neighbor. Likewise, these 2 guys are neighbor. These 2. Do we have neighbor between these? No. It is not full mesh, partial mesh. Okay, partial mesh. So what do we see here? The route learned via an IBGP are never propagated to other IBGP. What will happen if it is propagated? See what happens. Because you got LAN, when B send an update, It will go to everyone. Let's not talk about full mesh or partial mesh. That may confuse you. Better understand. They're all neighbors. They're all neighbors. Now we are trying to understand why this rule. Don't focus on anything else. Why we have this rule? Route learned via one IBGP never propagate to another IBGP. Why? You see, this guy is sending update 10 network. It goes to everyone. All have learned 10 network because you got one LAN switch. It can easily reach here. Same way, it can also reach here. It can reach here if they are neighbors. It gets delivered to everyone because they're all neighbors. Now, what will happen if C again advertises the same thing to E? And what will happen if E advertises the same thing to C, which it received from B? Duplication. They have already learned it, but there is going to be a duplication if C and D. See, a route learned from an IBGP, if it is again propagated, there's going to be a duplicate because E has already learned from B via layer 2. If one IBGP propagates to another IBGP, that's going to be duplication in this topology. This is what most of the time we see as a topology in the real world. So, we have this rule to prevent that looping duplicate updates. There won't be duplicate updates, there won't be loop. So, this rule is good. It may not be good in our topology. Did you understand the rule, this default rule and solution? Why full mesh?
Yes.
Fine. So we have seen in these 3 pages something very important. One is you cannot redistribute. Not a good idea. Not recommended. The other one is because there's a black hole in the middle. We need to run BGP on every router. And if you're running BGP on every router, it needs to be full mesh BGP session because IBGP split horizon rule says the route learned from one IBGP should not be given to other IBGP. Right? So this chapter is explained very well. Let's go back to our lab, yesterday's lab, where we are going to see something more deep. I'm going to start sniffing between these two routers. Before I start the router, I would like to sniff using Wireshark. Okay, the link is not up. Okay, fine. I'll quickly on it and immediately I'll run because I want to show you every single packet. That's why I want on right now before the conversation begins between them. And now I'll also go to the CLI. Still no packet have come, so that's why it is blank. Don't worry, it's booting now. Now only the booting is almost getting over, and then they will start do the conversation, BGP conversation, which we configured. If I forgot to save it, then I need to do it again. It's okay now. Let me go to R4 to get the console. Show IPBGP, show IPBGP summary. Okay, it is still idle. What about this interface? Show IPBGP summary. Okay. Okay, there is no configuration here. I think I did not say there is only IBGP configuration. I'm going to configure router BGP 1000. The neighbor is R4's address. What is R4 address? Show IP interface brief. It's 200.0.0.2. This one. Remote AS is what? Do you remember? It's 2000. 2000.
2000.
Now, listen carefully. As soon as I hit enter, you see what is going to come now. It's going to come now. The conversations will be, first it will begin with TCP conversation, then the BGP. Why it's not coming? Oh, it's already up. So there's some issue with the Wireshark. I'm going to shut down the interface, the ports, and restart the Wireshark again. Okay, I'm going to shut down those interface F00 so that right from the very first packet we can see. Okay, the peering is gone down, interface has gone down. Now I would like to start the capture. And now I'll say no shutdown on both sides. Come on. I just said no shutdown. No, whatever comes now, from now only you need to see. See, ARP request is going. Okay, good. Everything is done. I'm going to stop. You see, ARP request is going. Router 4, I believe, the EBGP on the right. What is that number? 4. Router 4 is sending who is 200.0.0.1 because it wants to form neighbor. Because it wants to form neighbor, it is asking ARP, tell me. It's a layer 2 broadcast. You see FFFFFF. It's an ARP request. Inside the request, if you see the payload, it says, who is this 20.0.0.1? I don't know the MAC address. Give me the MAC address of this guy. And this is my MAC address. R4 is saying this is my MAC address of this IP. So that's an ARP request. And then ARP reply comes as an ARP reply. This is the MAC address of 10.0.0.1. This is a reply. Reply is a layer 2 unicast. It's an ARP reply. Using that, you see, three-way handshake starts. First, who is initiating? R4 is initiating a TCP connection. It's not BGP, but port number you see 178. It's BGP only. On behalf of BGP, TCP initiates this. Port number is 179. See, it says I'm coming from so and so IP address, and this is the port number, and this is a SYN packet. That's very important. We need to focus. Flag is what? SYN. If you go inside, you can see SYN is turned on. SYN is set to 1. It's a SYN packet. As a response, if you see from the next packet, SYN is set as well as acknowledgement is set. SYN ACK is coming from router 3 to 4. And then ACK is going from router 4 to 3. Three-way handshake is over. After three-way handshake only, the open message is sent, keep alive message is sent, notification is sent. All right, and then updates are pushed and so on. All right, once in a while, keep alive will be sent. It will keep sending SYN and SYN-ACK and so on. See, SYN and SYN-ACK sent. So, what do we see here is, it is first the TCP and then the BGP packet. Only then the successful neighborship will come. We learned about these message types. Open message, keep alive message, notification message. We saw that in the previous day before class. Do you have any question? All right.
No, sir.
So then we should stop here.